You might think pumping liquid into a plastic jug is a pretty straightforward gig, right? Well, when you're dealing with massive volumes of highly concentrated agricultural chemicals, it is anything but simple. Just to wrap our heads around the sheer scale of this challenge, look at the global footprint. In 2024 alone, a staggering 209.8 million hectares of genetically modified herbicide-tolerant crops were planted worldwide. That is an astronomical amount of land. And that demand? That's exactly what drives this massive, multi-billion-dollar agrochemical industry that literally has to run around the clock just to keep up.
But here's the thing. Long before these chemicals ever make it to a farm, industrial engineers have to solve an absolute nightmare of a puzzle. I mean, think about it. How do you safely package a chemical that can literally eat right through solid metal and generate explosive gases while doing it? It takes a crazy delicate balance of chemistry, fluid dynamics, and metallurgy to pull it off.
So, let's jump straight into Section 1, the chemistry of weed control.
To figure out how to package this stuff properly, we really need to understand how it's built from the ground up. In its raw form, glyphosate is just a weak acid, and it actually doesn't dissolve very well in water. So, to whip up a super-concentrated liquid, chemists have to neutralize it with an alkaline base, which turns it into a soluble salt. Now, you'll often see active ingredient on a label, which includes the heavy weight of that salt, but the acid equivalent? That's what measures just the parent acid. That's the actual weed-killing muscle. And since different salts have totally different weights, engineers absolutely rely on that acid equivalent to standardize their concentrations and properly calibrate all the packaging machinery.
All right, moving on to Section 2, battling the foam crisis.
See, the raw herbicide by itself just rolls right off a plant. So, to make this chemical actually stick to and penetrate a waxy leaf, engineers pump it full of aggressive surfactants, which, if we're being honest, are basically just heavy-duty soaps. But this leads to our very first industrial headache, the foam crisis. Imagine pumping a liquid loaded with soap into a bottle at incredibly high speeds. It traps air, instantly. This creates these really persistent, thick foams that just overflow the containers, totally mess up the dilution ratios, and bring production line speeds to a grinding halt. You're left with uneven dosing, massive product waste, and just a terribly sticky, hazardous mess all over the factory floor.
So how exactly do they fix that mess? Well, the chemical solution is to introduce highly active defoamers like Invino 2200, and this right here perfectly showcases the sheer magic of chemical engineering. I mean, they use a microscopic 0.05% dose of this stuff. That tiny drop immediately migrates straight to the bubble